Hello, good day, students. I welcome you to your favorite YouTube channel, Physics for Everybody. Today, we'll be taking the Cambridge IGCSE Physics 0625 Paper 2 Variant 1 of the October-November 2023 exam. And without delay, let's go straight to the questions. Question number 1. Which is a vector quantity? A. Density, B. Mass, C. Pressure, D. Weight. Vector quantities have magnitude and direction, okay? And you know that weight acts downwards, okay, towards the center of the earth, yeah? So if you have an apple, the apple goes downwards, okay, as if it's going towards the center of the earth. So since the weight is directed towards the center of the earth, then weight is the one that has direction. Hence, weight is the vector quantities, while the rest are scalar quantities. Question number 2. The graph shows the speed of a car traveling through a town. Which section of the graph represents the period when the car is decelerating? Look at the first part. We have uniform acceleration. Okay, this is a distance of speed against time. So we have uniform acceleration. Then we have this exponential curve here that shows that acceleration is not uniform. Then we have zero acceleration. That means it's constant speed. Yeah, the body is traveling at a constant speed. Then what do you have here? Negative acceleration, which represents deceleration. That makes D the correct answer. Number 3, an object reaches terminal velocity after being dropped and falling through the air. Which graph shows how its speed varies with time? Speed against time. Okay, we have uniform acceleration, then we have this constant speed here. But take note of this sharp change here. When you have terminal velocity, there won't be this constant change, this sharp change rather. It won't exist. Okay, so the graph will just be a smooth transition from uniform velocity, okay, then from uniform acceleration, the acceleration decreases smoothly till it becomes zero acceleration, which is constant speed. This constant speed is called terminal velocity. So C is the correct answer because it's one that shows this smooth transition from uniform acceleration to um, a reduction in acceleration. So acceleration begins to reduce smoothly till the acceleration becomes zero, and in which case we consider the object to be traveling at uniform velocity. Yeah, when acceleration is zero, velocity is uniform, which means C the correct answer. There's a sharp transition here, hence this do not represent terminal velocity. Question number 4. The table shows the mass and volume of three different liquids X, Y, Z. The liquids are placed in the same container. The liquids do not mix. Which liquid is at the top of the container and which liquid is at the bottom? So if you have those three liquids and you have a container like this, okay, so those liquids will form layers because the liquids do not mix, okay. So the heaviest one, sorry, the most dense liquid will be at the bottom, okay. So, and the liquid with a medium density would be in the middle. The liquid is moderate density, okay. And the liquid with the least density will be at the top. So I use three different colors for that: blue, green, and red. So I use so if you look at this, now let's calculate the density of each of those liquids. How do you get the density of the liquid X? Density is mass divided by volume. So let us calculate the density of each of those liquids. For the liquid X, the mass is 120, volume is 200. Let's calculate the density. Density is mass, which is 120, divided by volume. Volume is 200. 120 divided by 200, we have 0.6 gram per cm cube. Let's calculate density for liquid Y. Density is mass. The mass of Y is 80 divided by the volume. The volume is 67. 80 divided by 67. Let's use our calculator to compute that. 80 divided by 67. 80 divided by 67. That gave us, sorry, I multiplied. 80 divided by 67. That gave us 1.19. So we have 1.19 gram per cm cube for Y. Let's do that for Z. Density is mass over volume. the mass is 100, volume is 120. Let us divide the mass by the volume. 100 divided by 120. 100 divided by 120. 0.833. 0.833. So which one has the least density? This 0.6 gram per cm cube. That is X. X has the least density, so it stays at the top, followed by Y, which has the moderate density 0.833. That is Y. Then the one with the highest density, sorry, X has a density of 0.6, so X stays at the top, the least density. So I've put X here. What about the second one in terms of density? This represents density. The next one is this is the next value. After 0.6 followed by 0.833, then 1.9 is the highest. So this is the next density after 0.6, 0.833, that is Z. Okay, and then the one with the highest density is Y, which is 1.19. You know, 1.19 is the highest density. So X stays at the top, Y stays at the bottom. Let's see, at the top X, looking at the bottom Y. Okay, A is the correct option. Okay, yeah. Then we go straight to question number 5. Which moving object has a resultant force acting on it? Sorry about that. Which moving object has a resultant force acting on it? A. A diver rising vertically through water at constant speed. You know, yeah, constant speed. When speed is constant, that simply means acceleration equals to 0, right? And you know, when you talk about resultant force, force equals to mass times acceleration. So if the acceleration is 0, mass multiplied by 0 gives you 0. Automatically, the resultant force is 0. Whenever you have a constant speed, it simply means acceleration is 0. And if acceleration is 0, automatically the resultant force will give you 0. So here to option B, an aircraft circling an airport at constant speed. Yes, when you have an object moving around a circular path, okay, let's assume an aircraft, let's assume this is the aircraft moving around an airport in circular path. When you have an object moving along a circular path, there's an acceleration that is directed towards the center of that circular path. That acceleration is called centripetal acceleration, okay? And as a result of that centripetal acceleration, there is a force centripetal, okay? A centripetal force acting on the aircraft, and that centripetal force is directed towards the center of the circular path, okay? Just the way there's a force that directs the moon towards the center of the earth, gravity, and that's a gravitational force. Okay, there's a gravitational force of attraction between the moon and the earth, and as the moon is moving around this circular path, okay, there's a force that tends to balance that gravitational force of attraction, centrifugal force. So in this case too, when you have this aircraft moving around a circular path, there's a centripetal force which is directed towards the center of the circular path. Okay, so that centripetal force is the resultant force. An aircraft circling an airport at a constant speed. Fine, speed is constant, but because it's moving along a circular path, there's a centripetal acceleration. Why? Because direction keeps changing. Direction keeps changing because it's moving around the circular path. So that change in direction automatically means there's a change in direction of the velocity. Fine, velocity is constant, but there's a consistent change in the direction of that constant velocity. That change in direction of velocity automatically means there's an acceleration. Yeah, so that means B is the correct answer, okay? Because that's centripetal acceleration. If you multiply it by time, by mass rather, mass times acceleration, that means force, okay? Yeah, that's what causes the centripetal force. As long as there's an acceleration, there will be a resultant force. Understood, right? If it's not understood, please rewatch this question 5 again. Number 6. Forces are applied to four identical objects. The length of each arrow indicates the magnitude of the force. Which object is in equilibrium? Okay, here we have the arrow looks equal, the arrows look equal, but these two forces are collinear. These two forces are collinear, okay? Or you say they are coplanar. Why do you say they are coplanar? Because fine, they act on the same plane, okay? And if you try to draw a line through those two forces, it passes right through the two of them, okay? If you draw a line through these two forces, it passes through the center. But if you try to draw a line through these two forces, no, we can't draw a straight line through these two forces. These two forces are not collinear forces. This simply means they will cause a rotation. These two forces will cause an anticlockwise rotation. Yeah, because we can't draw a straight line through the line of action of the two forces. Hence, this object is not in equilibrium because there will be an angular acceleration. This one too, these two forces are not acting on the same plane, okay? They don't have the same line of force. So they will cause, I'm talking about these two forces, okay? So they are not acting along the same. So if this is the center of mass of the object, these two forces will cause rotation about the center of mass. Same here, if this is the center of mass of this object, this force here and this one here would cause an anticlockwise rotation. Even though these two are balanced, these two will cause a rotation. So A and C are not balanced because of that. And in this case, the upward force is greater than downward force. Okay? Yeah, so this one too is not in equilibrium. This is the only one in equilibrium. The forces are balanced. Due to these two forces not being balanced, the resultant force will never be equal to zero. Hence, the object is not in equilibrium. Here, the resultant moment will not be equal to zero. That's why it's not in equilibrium. Here too, the resultant moment is not equal to zero. Hence, A is not equilibrium. B is the only one in equilibrium because the resultant force equals to zero and the resultant moment equals to zero. Understood? Question number 7. A sphere X collides head-on with a second identical sphere Y, which is stationary. The mass of each sphere is 0.15 kilogram. Sphere X traveling at a velocity of 2 meters per second before the collision, sphere X is traveling at a velocity of 2.0 meters per second before the collision and produces an impulse of 0.21 Newton second. The sphere X produces an impulse. Now, what is the velocity of sphere X after collision? Okay, so we have to analyze what is happening here. We have a sphere and we call it the sphere X. And we say, X, yeah. And we say this sphere is traveling at a velocity of 2 meters per second. It has a mass of 0.15 kilogram. Now, it collides with another sphere, Y. Y has the same mass of 0.15 kilogram and the initial velocity is zero, is stable. After impact, once the two of them collides, what do you think will happen? Both of them will move in the same direction. Okay, good. Okay, both of them will move in the same direction. That is what will happen. Why? Because the sphere Y, it is a sphere, it is free to revolve. So once it experiences an impulse, it will definitely move, okay? So X will also move along its path, but with a changed velocity. Why? Because there's collision, there will be a change in momentum. But let's assume that this sphere X collided with sphere Y, both of them traveling towards each other at um, probably equal velocity, fine. After collision, they might bounce back. After collision, they might bounce off each other and travel in opposite direction, okay? But in the case whereby this sphere Y is stable, it's not moving this way, it's stable, which was this case. It has a velocity of zero. After collision, both of them will move forward with a velocity lower than the initial velocity of X. So how do we get the final velocity with which X moves forward after collision? Now we have to analyze the question this way. How do you get the final velocity here? Now you know that when X collided with Y, there was a change in momentum, okay? And that change in momentum is equal to the impulse. Impulse equals to change in momentum. Okay, and the formula for change in momentum is mass multiplied by the higher momentum minus lower momentum. What's momentum of X before collision? The momentum of X before collision will be higher than momentum of X after collision. Why? Because it's giving part of its momentum to Y. Y had zero momentum because it was at rest. But after collision, Y gains some momentum from X. That simply means X loses some momentum. If something is losing momentum, it means the final velocity will be lower than initial velocity. So if you are calculating change in velocity, it will be initial velocity minus final velocity. This is what happens when final velocity is less than initial velocity. So if you are calculating change in velocity in a situation whereby velocity is reducing, the change in velocity will be initial velocity minus final velocity. What's the mass of object X? Mass of object X is 0.15 kilogram. What's the initial velocity of object X? Initial velocity of object X is 2 meters per second. Final velocity of object X is unknown, but the impulse of object X is 0.21 Newton second. Now let's substitute. Impulse, which is 0.21, equals to mass, mass is 0.15, open bracket, initial velocity is 2, minus final velocity, we do not know, V. What do we do here? We divide both sides by 0.21. Sorry, we divide both sides by 0.15. Why? Because we want 0.15 to cancel out from both sides. So 0.15 will cancel out on the right hand side, rather, yeah? So 0.21 divided by 0.15, let's use our calculator. 0.21 divided by 0.15, that gave us, sorry, 0.21. 0.21 divided by 0.15 divided by 0.15, that gives us what? 1.4. So we are using 1.4 here. So 0.21 divided by 0.15 gives us 1.4. 1.4 will be equals to 2 minus V. How do we get V? Okay, if I bring V here, it becomes plus. Then if I bring this 1.4 to the right hand side, it becomes minus. So V equals to 2 minus 1.4. 2 minus 1.4 gives us 0.6. And do not forget that in our analysis, we analyzed the problem and said that that the object X will travel in the same direction. It will travel in the same direction. Both X and Y will travel in the same direction. So our answer for final velocity of object Y, for final velocity of object X rather, will be 0.6 meters per second in this same direction. So let's look at our option 0.6 meters in the opposite direction to Y, 0.6 meters per second rather in the same direction as Y. B is traveling at the velocity of 0.6 meters per second in the same direction as Y. We go straight to question number 8. Let's go. A cyclist travels down a hill from rest at point X. A cyclist travels down a hill from rest at point X without pedaling. The cyclist applies his brakes and the cycle stops at point Y. Which energy transfers have taken place between X and Y? Okay, since the cyclist was at rest here, and you see, and it's going from X to point Y, look at the point X, it has a certain height above point Y. Yeah, it has a certain height above point Y. If you judge, yeah, so it has a certain height above point Y. When an object has a height above ground level, then it is said to have a gravitational potential energy, which is given by mgh. Yeah. So it has gravitational potential energy at X, and at Y, it is at rest. Okay, it stops here. So what has happened to gravitational potential energy? It has changed to thermal energy or heat energy. Yeah. And in the midway, the object was moving midway. Okay, sorry, the cyclist was moving midway. So it's said to have kinetic energy while he's moving. So that's energy transformation that takes place there. Okay, gravitational potential energy changes to kinetic energy, and then kinetic energy changes to internal energy. That makes option A the correct answer to question number 8. Question number 9. An object of mass m falls from a higher shelf to a lower shelf. This object falls from higher shelf to a lower shelf. How much gravitational potential energy does the object lose? So how much gravitational potential energy? How much energy will be lost from here to here? So how do you get the change in energy? The change in energy is just gravitational potential energy at the top position minus gravitational potential energy at the lower shelf. Gravitational potential energy at the higher shelf is mgh. What's the height here? H1. The height here is H1, okay? And gravitational potential energy at the lower position is mgh2. Okay, the height down at the of the lower shelf is H2. Okay, so the change in energy from here to here will be mgh1 minus mgh2. mgh1 minus mgh2. What is common? Mg is common. What will be left? H1 minus H2. That makes option D the correct answer. Yeah, that's how you get the change in energy. Question number 10. A pump does 460,000 joules of work to raise water to fill a tank. It takes 7 minutes to fill the tank. What is the power of the pump? What's the formula for power? Power is equal to work done divided by time. Okay, but take note that power here is recorded in kilowatts. Look at all the options here, kilowatts. So we have to change our work done from watts to kilowatts. You know, the work done is 460,000 joules. You have to change the unit of our work done from joules to kilojoules rather. So change 460,000 joules to kilojoules. It means you divide by 1,000, and that will give you 460 kilojoules. That's the work done, 460 kilojoules. And what's the time? Time is 7 minutes, right? If you are converting minutes to second, what will it become? Convert minutes to second. You multiply it by 60. So you have 7 multiplied by 60. That will be 420 seconds. So to now get the power now, okay, the power is now work divided by time. Our work in kilowatts divided by our time in seconds. Sorry, our work in kilojoules divided by our time in seconds. Our work in kilojoules is 460 kilojoules. Time in seconds is 420 seconds. 460 divided by 420, what would that give us? Let's see. 460 divided by 420. That gave me 1.09, which is approximately 1.1. So my answer is approximately 1.1 kilowatts. That makes option A the correct answer. Okay, take note that that kilo came from the division of the work done in joules by 1,000. When you divide by 1,000, you get the work done in kilojoules. Kilojoules divided by second gives kilowatts. Question number 11. The water in a swimming pool exerts a pressure at the bottom of the pool. Which graph shows the relationship between the pressure exerted by the water and the depth of water in the pool? So pressure, assume the density of the water is constant. Yeah, you know, pressure in fluid, pressure in liquid and gases is density multiplied by gravity multiplied by height. So that simply means provided that density is constant, and you know gravitational field strength on the earth is always constant. Yeah, so this simply tells us that pressure is directly proportional to height. That's what this tells you. Pressure is directly proportional to height. That simply means if height is increasing, pressure must be increasing. And if height is decreasing, let me use color red for decreasing. When if height is decreasing, then pressure must also be decreasing. And which graph shows us that? Direct proportionality. This is not direct proportionality. This is an exponential curve. Okay, like pressure is proportional. Like pressure is proportional to square root of height. This is the kind of graph you have. And something like this will be pressure is proportional to height square. Okay, that's this exponential rise. But this straight line means pressure is just directly proportional to height, which is option C. Okay, option C, that's the only place where you have straight line. Pressure is directly proportional to height. Option D, this one here, means pressure is inversely proportional to height. Okay, yeah, that's what this negative slope here shows. So C is the only correct answer to question number 11. We go straight to question 12. Why can a gas be compressed easily into smaller volume? A. The particles are far apart. Excellent. That's the correct answer. You can only compress a gas because the particles are already far apart. Okay. So if these are particles, they are far apart. By the time you put them in a container, okay, and apply pressure using this piston. If you apply pressure, you try to press it, what happens? You successfully compress the liquid to occupy a smaller volume, and all the particles will gather together. All the particles will gather together and occupy a smaller volume. I'm talking about something like this. All the particles will gather together and occupy a smaller volume. All the particles will be here. So that's what we mean by compressing a gas. So initially, the particles are far apart. So when you try to press them, compress them and press them together, the particles will come together and occupy smaller volume. Okay, initially they were far apart. Okay, by the end, what happens? What happens? They will come together and occupy smaller volume. That's what I mean by applying pressure on the gas. So that makes option A the correct answer to question number 12. Goes to question number 13. Oh, good, good. A gas is a gas is contained in a cylinder by a movable piston. A gas is contained in a cylinder by a movable piston. Okay, so the gas is in this place. The gas is heated, so it expands at constant pressure. If the gas is expanding at constant pressure, it simply means this piston will be moving backwards to ensure the pressure is constant. Now, how is the force of each collision of gas particle with the piston affected, and how does the frequency of collision between the gas particles and the piston change? When you apply heat, pressure increases, fine. The piston will pull backwards. That simply means the distance between each of the molecules will increase. So if the distance between the molecules increases, you know, when you compress the gas molecule, the distance between the particles reduces. Before compressing, the particles might have had this kind of distance, this kind of spacing. Yeah, they must have had meaningful space between, yeah. Particles might have looked like this before compressing. But after compression, the particles come close together. That simply means the space between the particles reduces when you compress. And if the spacing between the particles is reducing, it simply means collision will be less frequent. For instance, look at this particle. It quickly collides with the wall of the container and bounces back. But when they are spaced apart, this one, it takes longer time before it collides with the wall of the container and bounce back. It takes longer time for each particle to collide with the wall of the container and bounce back. That means collision becomes less frequent. Okay, yeah, frequency of the collision will decrease, fine. What about the force? What happens to the force? Since increasing the temperature of the gas molecule means you are increasing the kinetic energy of the particles. I know energy has the same unit as work, which is force times distance. So if the kinetic energy of the particle is increasing, it simply means the force with which they collide with the walls of the container will increase. So force must increase while the frequency of collision will decrease, which makes option A the correct answer to question 13. We go straight to question 14. On a warm day, a carton of fresh milk is covered with a wet cloth. Why does this help to reduce the temperature of the milk? Hmm. Okay, so when you have a the cloth has moisture, okay, water molecules. What happens? On a hot day, there will be evaporation. The water molecule becomes gas. But take note that during evaporation, highly energetic particles close to the surface would escape. And as the energetic particles are escaping, what happens? The less energetic particles will be left on the cloth. And less energetic particles simply means they have less kinetic energy, which means they have less temperature. Temperature will be reducing. Do not forget that temperature of a liquid is a measure of the average kinetic energy of its particles. If temperature is less, it means the average kinetic energy of the particles will be less. And if temperature is high, average kinetic energy of the particles will be high. Yeah, so during evaporation, that explains cooling by evaporation. During evaporation, as the energetic particles are leaving, the temperature of the liquid, okay, eventually reduces. That simply means temperature of the liquid that soaks the clothes reduces, and that could be cooling. That can be considered to be cooling the milk, ensuring the temperature of the milk does not rise, which makes option A the correct answer to question number 14. We go straight to question number 15. A chef, a chef heats some water in a pan on a hot plate. The temperature of the water rises by 10 degrees Celsius in time t. She then puts the same volume of oil in an identical pan, on the same hot plate. What next? The specific capacity of water is 2.5 times that of oil, and water is 1.1 times denser than oil. What is the time for the temperature of the oil to rise by 10 degrees Celsius? What will you do here? You know, she's supplying thermal energy to the water, right? Good. And later, she replaces the water with oil, right? Good. So the thermal energy she supplies can be given by the formula H equals to mc change in theta. Yeah, quantity of heat is mass times specific capacity times change in temperature. So let's go. For the water, quantity of energy, okay, you know the formula for quantity of energy, Q, is equals to mc change in temperature, right? Good. So for the water, quantity of energy she supplies to the water is mass of water, right? And times specific capacity of water times change in temperature of water. And for the oil, quantity of energy she supplies to the oil is mass of oil times specific capacity of oil times change in temperature of the oil. Okay, yeah, so let's use this to analyze this problem. Now let's go. Do not forget that the specific capacity of water is 2.5 times that of oil. So specific capacity of water is 2.5 times specific capacity of oil. Also, oil and water is 1.1 times denser than oil. Water. So that simply means density of water, you know, density is mass over volume. Since the volumes are equal, then the densities can be considered to represent the mass, okay? Okay, to a reasonable extent. Yeah, within the limits of this accuracy of this experiment. So that simply means mass of the water will be 1.1 times mass of the oil. Yeah, since the water is 1.1 times denser than the oil. Now let's go. And the change in temperature in each case, change in temperature for oil, change in temperature for oil is 10 degrees Celsius. Change in temperature for water, change in temperature for water is also 10 degrees Celsius. Now, how do you get the quantity of thermal energy supplied? Quantity of thermal energy supplied to the water, quantity of thermal energy supplied to the water is mass of water times basic capacity of water times change in temperature of water. What's mass of water? 2.5 times mass of water is 1.1 times mass of oil. Okay. We know we've expressed the quantity of energy supplied to the water. What about quantity of energy supplied to oil? Quantity of thermal energy supplied to the oil is mass of oil, specific capacity of oil, times change in temperature of oil. Let's do that, which is a mass of oil, specific capacity of oil, change in temperature of oil is 10, right? Times 10. Yeah. What about quantity of energy supplied to the water? Quantity of energy supplied to the water is mass of water. Do not forget that mass of water is 1.1 times of mass of oil. So you have 1.1 mass of oil times space capacity of water. Space capacity of water is 2.5 times space capacity of oil. 2.5 times of space capacity of oil. What about the change in temperature? Change in temperature is 10 degrees Celsius in both cases, times 10. Okay. Yeah, so that simply means quantity of energy supplied to the water would be 1.1 times 2.5, that would be 2.75. That would be 2.75, multiply it by 10, that would be 27.5. That would be 27.5 times mass of oil, space capacity of oil. What about quantity of energy supplied to, sorry, yeah, we didn't, yeah. What about quantity of energy supplied to the oil? Quantity of thermal energy supplied to the oil is mass of oil, space capacity of oil times 10, right? Yeah, that will be 10 mass of oil, space capacity of oil. That's quantity of energy supplied to the oil. The reason why we are using these variables is because we want to consider the rate at which heat was being supplied. Since you are placing both of them on the same hot plate, and the hot plate supplies energy at the same rate, okay, and the rate at which energy is being supplied represents what? Power. Power is the rate at which energy is being dissipated. Yeah. Now, the power supply to the oil will be equal to power supply to the water. Yeah, good. And what's the formula for power? Power is quantity of heat divided by time. Okay, that simply means quantity of heat supplied to the oil divided by the time for the temperature of oil to rise must equal to quantity of heat supplied to the water divided by time taken for the temperature of the water to rise. What's the question? What is the time for the temperature of the oil to rise by 10 degrees Celsius? We're looking for time for the temperature of the oil to rise. How do you get time for temperature of oil to rise? The time for the temperature of oil to rise equal to what? To make this one the subject, it becomes quantity of heat supplied to water multiplied by time for temperature of water to rise divided by quantity of heat supplied to water. Yeah. Okay, to make this one the subject, time for temperature of oil to rise equal to Q0 multiplied by TW divided by QW, which is what we have here. Yeah, so time for temperature of oil to rise is quantity of heat supplied to oil. What is quantity of heat supplied to oil? That is 10 times mass of oil, space capacity of oil. Time taken for the temperature of water to rise. You were told that the temperature of water rises by 10 degrees Celsius in time T. So time for the water is T, okay? Temperature of water to rise by 10 degrees Celsius for water. So time for water is represented by alphabet T, fine. Divided by quantity of heat supplied to the water. Quantity of heat supplied to the water is 27.5 times mass of oil, is basic capacity of oil. So what's next in here? We can cancel out. Let's cancel out. Mass of oil cancels out, basic capacity of oil cancels out. What's left? Time taken for the temperature of oil to rise. Let me return to color blue. Time taken for the temperature of oil to rise is what? 10 over 2.75 of T, where T is time taken for the temperature of oil to rise. So if you do 10 divided by 2.75, sorry, is it 2.75? No, this is 27.5, not 2.75. 10 divided by 27.5, okay, and then I multiply that by T. 10 divided by 27.5. So let me use my calculator to divide 10 by 27.5. 10 divided by 27.5. 0.3636363636. So two decimal places. I will have time for temperature of oil to rise becomes 0.36 times T, where T is time for temperature of oil to rise, which makes option A the correct answer to the question. Please, if this calculation looks complex to you, you may have a break, okay, and return to watching the video later. Okay, yeah, and you have free online free online sessions which you can join. Okay, just send an email to me. Send an email to me so I can add it to your Google Classroom. We have free classes to prepare you for the real exam, for your exam. Few days to your exam, I'll send a message to you. Rather you email me, send an email to me. To the next question. The diagram shows the view of a room heated by a radiator. This is a radiator. The arrowed line from X to Y, the arrowed line from X to Y is the part of the convection current in the air. Convection current in the air goes this way. Which arrow about the air temperature and the air density at X and at Y is correct? What's the air temperature at X and what's the um, air density at Y? Let's see. Air temperature higher at X. Is temperature higher at X? Yes. When air gets heated, it rises, okay? It becomes less dense. It becomes hotter, fine, and it becomes less dense, so it rises, okay? Then it goes round and goes back to fall down at the other end of the container. Okay, so that means at this point where it's falling is because the at this place where the air is falling is because the air here is heavier, is denser, that's why it falls. Okay, then it comes here to get heated again and rises, and that completes the convection current. So here the air is hot and light, while here the air that's falling down here, it is heavy and cold. Okay, heavier means it's also denser. So at air temperature at higher at X, yes, air temperature is higher at X. Air density higher at X. Air density is not high here. Air temperature higher at X, yes. Air density higher at Y, yes. Air density is higher at Y. That makes option B the correct answer to question number 16. We go straight to question number 17. Yeah, question number 17. Two men P and Q stand close to a gap in the wall as shown. Man P cannot see the man Q, but the man P can hear the man Q. So this man P cannot see the man Q, but he can only hear him. Which statement explains this? Light waves do not diffract at all because they are electromagnetic waves. Light waves diffract, but only through tiny slits, very tiny opening. Okay, yeah. D. Light waves have a range of frequencies, but sound has just one frequency. That is wrong. Sound also has a range of frequencies. Sound waves are of a higher frequency than light rays. That is wrong. Light rays has very, very far higher frequency than sound waves. Sound waves diffract a lot because their wavelength is a similar size to the width of the gap. Excellent. So when the wavelength of the wave is similar to the width of the gap, there will be diffraction. Also, if the wave is coming and there's an obstacle on the part of the wave, okay? If the wave is coming, sound waves for instance, and there's an obstacle in the part of the wave, if the width of the obstacle is close to the wavelength of the wave, then there will be diffraction. You get it? There will be diffraction. So the waves begin to bend around the obstacle. So that is the concept of diffraction of waves. We go straight to question number 17. Which quantities relating to a wave on the surface of water can both be measured in meters? Amplitude, yes. Amplitude is the maximum displacement, okay? So since it's water wave, is not voltage or current, then the amplitude will be measured in meter because the height of the water, okay, let me use color green to distinguish between different parts of this diagram. The parts of this maximum displacement from here to here can be measured in meters. The amplitude can be measured in meters. What about the wavelength, the distance between two successive crests from here to here? This distance can also be measured in meters. Wavelength can be measured in meters, amplitude can be measured in meters. Okay, that makes amplitude and wavelength. Option B the correct answer. Let me return to color. Okay, we go straight to question number 19. Let me remove anything that can cause distraction. The diagram shows part of a ray diagram that demonstrates the formation of a virtual image Y. This virtual image Y of object X by a converging lens. One ray of light from X is shown. This is a ray of light approaching the lens. The ray of light approaches the lens. Which arrow shows the direction of the ray as it leaves the lens? Okay, if this ray gets to the lens, let's assume this is the principal focus. Let's assume this is the principal focus. What happened? The ray that passes through the lens, it just goes straight through the principal focus, follows this part. No, it's not passing through the principal focus. It goes straight through the principal focus, follows this part. Okay, so you can then decide to trace the ray backwards to get where it's coming from. That's what we mean by the ray passing through the principal focus. And that's how virtual images are formed by this lens. Okay, yeah. So which arrow shows the direction of this ray as it leaves the lens? This is the arrow that shows direction. So which of these arrow? It is arrow A that follows that same path. Arrow B goes this way, and the ray is not going this way, is it? No. So that makes B is wrong. Arrow C means the ray goes backward this way. Is the ray actually going back this way? No. It just appears as if it was coming from here, but it's not actually going that way in reality. And option D, of course not. The ray can definitely not go back this way. That's unrealistic. So, question number 19. A ray of light is reflected by a plane mirror. This is the plane mirror, this is the ray, incident ray, reflected ray. Which arrow shows the angle of incidence and the angle of reflection? Angle of incidence. This arrow shows angle of incidence. This arrow shows angle of reflection. So Q is the angle of incidence, okay? Which row shows the angle of incidence and the angle of reflection? So angle of incidence will be Q, angle of reflection will be R, Q and R. Angle of incidence Q, angle of reflection R. Option C is the correct answer to question number 20. Question number 21. A thin converging lens is used to produce a real image of an object. Which statement about the real image is always correct? Real image is nearer to the lens than the object. No, that's a virtual image. No. Virtual image is further to the lens than the object. Fine. But when you talk about real image, it is nearer. What is the question again? Yeah. Which statement about real image is always correct? It is nearer to the lens than the object. No, that's a virtual image. No. Okay, let me say option B. It is on the opposite side of the lens. Yes, that's correct. Okay, so real images is not always nearer to the lens. There can be instances where the real image will be far further from the lens. Option C, it is the same size of the object. Well, which statement about real image is always correct? It is upright. No, only a virtual image is upright. The image here is upright. That is a virtual image. Okay, let me see again. It is on the opposite side of the lens. Yes, a real image will always be at the opposite side of the lens. That's correct. And it is the same size of the object. Yes, a real image can also be at the same size of the object. Then it's on the opposite side of the lens. Of course, that's always correct. It's the same size of the object. Yes, a real image can be of the same size of the object. A virtual image can also be at the same size of the object. It is upright. Only a virtual image is upright. It is nearer to the lens than the object. Let me see. Look at the image here. Image nearer to the lens than the object. The image, no, this is a virtual image. Virtual image is further, real image. If it is forming a real image, okay, let me just start to analyze this question to get what it actually requires of us. So this is the lens, this is the principal, this is the principal focus, this is the principal focus here, this is the principal focus here. So when the ray goes the lens, it goes this way, another one that goes this way. I'm guessing it becomes parallel. Okay, Okay, yeah. So this is a virtual image, but it's also a magnified image. But real image will always be on the other side, okay? This is one side, the left hand side, and this is the right hand side. Real image will always be at the other side, okay? It is at the opposite side of the lens to the object. Yes, that makes us be the correct answer. This one is a virtual image because both the object and the image are on the same side, okay? But a real image, look at the real image, is at the other side of the lens, okay? And if you try to produce a simulation of the image formed, okay, if you come here, I don't know if I should use this or use this. Let me use this. So you use this PhET simulation. PhET simulation are a very illustrative tools for you to get to understand the concept better. Yeah. So when the simulation comes, let us pick the converging lens, okay? So real images would always be formed on the other side of the lens. You get it? The virtual image, both of them will be formed, the image will be formed on the same side. You can see dotted line, meaning it is a virtual image, okay? Okay. But once you have thick lines, real lines, then it's a real image. The real image here is magnified, so it's not every time that the image is diminished. But if the image is far away, if the object is far away from the lens, then the image can be diminished. Fine. But the point is that real image will always be formed on the other side of the lens. Why? You can see with thick lines to the image. The image, this is the image, blurred, while the object is the real one. While here, image is blurred. The virtual image is formed on the same side, okay? The dotted line shows you that it is virtual, and you can see it is upright. So this helps us to analyze the situation, okay? So real image will be formed on the other side of the lens. We go straight to question number 22. But let me just ship this in quickly, okay? So when you open this, you see the link, and this is my email address, okay? So just send a message to me to this email so I can have your email and add it to the Google platform, okay? Then you can have free revision classes 3 days to your exam, okay? 3 days, a day before it, and a day of your exam. All right, let's go. A radar transmitter broadcasts at a frequency of 200 kilohertz. What is the wavelength of these? What is the wavelength of these radio waves? What's the formula here? V equals to F lambda, okay, where V is the speed, F is the frequency, lambda is the wavelength. So to get wavelength, wavelength equals to velocity over frequency. Yes, what's the speed of all electromagnetic waves? All electromagnetic waves, okay, all light rays travel at the speed of 300 million, 300 million, okay, 1, 2, 3, 4, 5, 6, 300 million meter per second. What's the frequency? The frequency is 200 kilohertz, right? 200 kilohertz, 200 kilo means 1,000, 200,000 hertz. So what will be the answer here? 300 million divided by 200,000. What would that give you? If you divide 300 million by 200,000, you should get 3,000 divided by 2, which is 1,500. 1.5 times 10 to the power 3. Option C is the correct answer to question 22. We go straight to question 23. The element mercury exists as a solid, a liquid, or a gas. Which role gives a possible set of values of the speed of sound through mercury? You know, sound is fastest through solids. Yes, sound wave has its highest speed in solids and the lowest speed in gases because the molecules of gases are far apart. But the molecules of solids are close apart, so the molecules can easily and quickly collide with each other during their vibration and transmit the sound waves. But gases, molecules are far apart, okay? So the molecules have to travel long distances before there will be collision between one molecule and the next. So sound is fastest in solid and slowest in gases, while sound wave has average speed in liquid. So let's see, speed of sound in mercury, frozen. Okay, when mercury is in solid state, let's pick the highest value for solid. Okay, this will be for solid, and lowest value for gas. Okay, this is also where you have lowest value for gas. Then the moderate value, okay, the intermediate value will be for liquid. So that makes D the most reasonable question, the most reasonable answer to question number 23. We go straight to question number 24. Which metal could be used for a permanent magnet and which metal could be used for the core of an electromagnet? An electromagnet is a temporary magnet and we use soft iron. Good. While for permanent magnets, we can use um, alloys consisting of cobalt, manganese, nickel. Then we can also use steel. Steel is also an excellent metal to be used for permanent magnets. So to form a permanent magnet, we use steel, and for a temporary magnet, we use yeah, core of electromagnet. That's a temporary magnet. We use soft iron. Okay, iron. Yeah, iron. Good. So that makes option D the correct answer to question 24. Question number 25. Which statement describes the direction of an electric field at a point? And the electric field, the direction of electric field represents the direction in which an isolated positive charge will go if placed in the field. Let us consider this field that is made. Let's consider a uniform field between two plates of opposite charge. You know, the electric lines of force run from the positive um, charge, positive plate to the negative plate. So this represents the line of force. Okay. Now, if we drop an isolated positive charge in this field, in what direction do you think this positive charge will go? If I drop a positive charge here, what happens to this isolated positive charge, this free positive charge? There will be repulsion between these two because they are like charges. So there will be repulsion, and the repulsion tends to make this charge move to the right. Okay, because it's being repelled by this charge here. Now look at between this charge and this plate, there will be attraction, and that attraction tends to make this charge go this way. So that simply means the direction of the field shows the direction in which this isolated positive charge will go. Okay, so the direction of the field, this arrow here already tells us the direction in which this free positive charge will go. So let's see. It shows the direction of force on a negative charge, no. The direction of force on an endpoint, no. The direction of force on a positive charge. Excellent. Option C is the correct answer to question number 25. Let me return to color blue. Okay, go to question number 26. Which statement about a voltmeter is correct? It has a scale which is measured in amperes. Voltmeter measured in amperes. No. It must be connected in series to a circuit. That is ammeter. It measures potential difference. Excellent. Voltmeters measure potential difference. Question number 27. A wire has a resistance of 8 ohms. A second wire of the same material has twice the length and twice the cross-sectional area. What is the resistance of the second wire? Now we have to solve this question. We need some space. A wire, let's call that wire the wire number 1, okay, being the first wire we are putting into consideration. So wire number 1 has a resistance of wire number 1 is 8 ohms, right? Good. A second wire made of the same material. Okay, since they are made of the same material, that means resistivity of the first material must equal to resistivity of the second material. Okay, wire, yeah. A second wire made of the same material, okay, that means they have the same resistivity. That second wire has twice the length. So length of the second wire is twice the length of the first wire and twice the cross-sectional area. That simply means cross-sectional area of the second wire is twice the cross-sectional area of the first wire. What is the resistance of the second wire? The resistance of the second wire is unknown, but we know that the two wires have the same resistivity. Yeah, we know that the resistivity of the first wire must equal to the resistivity of the second wire. So how are we going to deal with this kind of question? We know very well that resistivity is rho L over A. Resistivity is resistivity, yeah, is RA over L rather, RA over L. Okay, and the resistivity of the first wire is equal to the resistivity of the second wire. Why? They are made of the same material. So that simply means RA over L for the first wire must equal to RA over L for the second wire. Yeah, so you say R1 A1 over L1, okay, that's first wire, equals to R2 A2 over L2. Yeah, so that's how we consider the two wires, okay? The first wire, RA over L, okay? RA over L for the first wire, then RA over L for the second wire. Now let's substitute. What's R1? 8 ohms. 8 times, what's A1? Area of the first wire. We don't have it, fine, we put A1 here. Over L1, what's the length of the first wire? We don't have it, fine, we put L1 here. Equals to, what's R2? R2 is the unknown that you are looking for. So we have R2. A2, what's A2? Area of the second wire is twice area of the first wire. 2A1 over L2. What's L2? Length of the second wire is twice length of the first wire. 2L1. Now we cross multiply. When we cross multiply, we have let me switch to different color to cross multiply. So we have R2 2A1 R2 equals to, okay, 2A1 R2 multiplied by L1. Okay, they say L1 here. L1 equals to 8A1 multiplied by 2L1. Okay, so what can we do here? A1 is common on both sides. You can cancel out. A1 is common on both sides. They can cancel out. What about length? L1 is common on both sides. They can cancel out. 2 is common on both sides. It can cancel out. What is left? R2 equals to 8 ohms. So the resistance remains 8 ohms. That makes option B the correct answer to question number 27. We go straight to question number 28. Let me remove anything that can cause distraction here. So question number 28 says, a plastic rod is rubbed with a cloth. The rod becomes positively charged. The rod becomes positively charged. This is the cloth. Okay, yeah. A plastic rod is rubbed with a cloth. The rod becomes positively charged because of the movement of charged particles. Yeah, if both of them are rubbed together and this one becomes positively charged, it's because electrons have left this rod. Electrons have migrated from the rod and have become part of the cloth, have become embedded on the cloth. That's what happens. Electrons migrate, they leave this place and they go to this one. So the rod will eventually be left with a net positive charge. So let's see. Charged particles that migrated the electrons, direction of movement from cloth to rod. No, from rod to cloth. Electrons move from rod to cloth. Excellent. That makes option B the correct answer to question number 28. We go straight to question number 29. An alternating current AC supply is connected to a diode and a resistor in series. Which graph shows how the potential difference V across the resistor varies with time t? So this is the alternating current AC power supply. This is the diode, this is the resistor. Okay, this is the AC power supply. This is the waveform that shows how AC varies with time. Now let's see, when the AC is supplied, what happens? The diode will be switched on during the positive half cycle. Okay, so the diode will be switched on and the potential difference, the voltage will be seen across the resistor. Okay, yeah, so during the positive half cycle, diode will be switched on successfully. During the negative half cycle, this one becomes positive, this one becomes negative. Okay, and the diode will now be reverse bias, it will be off. So the negative half cycle, this negative half cycle will not be seen by the diode. Okay, it won't exist. It won't exist. It won't be seen across the resistor. It won't exist across the resistor because the diode is reverse bias. So during the third half cycle again, this becomes positive, this becomes negative. The diode will be positive, it will be in forward bias, and the voltage will be seen across the resistor. So this will be successful. During the fourth half cycle, this becomes positive, this becomes negative, diode becomes reverse bias, and the voltage will not pass through, it will not be seen across the resistor. So fourth half cycle will not exist. So we only have first, third, and on and on and on, which is the shape of the waveform option C. Look at the four options. That option C, that's what gives us what we analyzed here. Okay. Yeah. Only the first half cycle, third half cycle, second will not exist, fourth will not exist, sixth will not exist, on and on and on. We go straight to question number 30. The diagram shows a circuit used to switch on a heater when the temperature drops below a certain value. Now, this is the heater. Okay, this is the heater. Thermistor is the heater. Okay, and this is what? This is a relay. Yeah, we are using this motor to switch on the current flowing through the heater. Okay, and this is the AC power supply. This is a very practical system here. Yeah, which row shows the components that should be connected at X and at Y? Now you want to switch the heater when temperature drops below certain value. That means you are monitoring the temperature of the environment. Once temperature is low, this one should be switched on so that current can flow through the heater and heat the environment. When temperature is high, it will now be switched off. So what should be here that is controlling the switch, that's this relay, should be something that reads temperature. So that when temperature is high, it switches it on so that current can flow through the thermistor. This is thermistor, the heating element. When temperature is low, it will switch it on. Okay, so it wants this one to be able to receive high voltage and switch on this switch when temperature is low, and receive low voltage so that it won't be able to switch on this switch when temperature is high. And what is that element that will have low voltage when temperature is high and high voltage when temperature is low? That is a temperature dependent resistor. A temperature dependent resistor. This is a resistor whose resistance depends on temperature. When temperature is low, the resistance here will be high. Okay, and from voltage the resistor, that means you must have a constant resistance here, a constant resistor. Okay, we have a fixed resistor here, then we have the temperature dependent resistor here. So that when temperature is low, the um, resistance here will be what? High. Once the resistance here is high, it means high voltage will be across this component. Since if the voltage here is high, that means high voltage will exist across the relay, okay, and it will switch on this thermistor. When temperature is high, when the thermistor works for some time and temperature is high, what happens? The resistance here will reduce. At high temperature, resistance here reduces. And once resistance here reduces, what happens? It means voltage here will be lower than what is required. Okay, voltage here will be higher than voltage here. So that simply means it won't be able to switch on the relay. Okay, yeah. So that is what we have here. X is a resistor, Y is a temperature dependent resistor, which means option B, the correct answer to question number 30. We go straight to question number 31. Yeah, question number 31 says, a current in a solenoid produces a uniform magnetic field inside the solenoid. The magnetic field direction is due east, which changes will produce a stronger magnetic field with a direction due west. Initially, direction is due east, so we only want to reverse the direction and increase the strength of magnetic field. Let's see. Using smaller current, we only make magnetic field weaker. Using smaller current, magnetic field will be weaker. Using larger current, yes, magnetic field will be stronger, and then turn the solenoid through 90 degrees. You don't use 90 degrees, it's 180. Okay, because you want to change the direction, so not 90 degrees. Use larger current, yes, magnetic field will be stronger. And reverse the current, yes. If you reverse the direction of the current, then the direction of magnetic field will be reversed. So that makes option D. Okay. Either you say reverse direction of current, or you turn it by 180 degree. That simply means you are turning the direction. Okay. Yeah, that's angle 180 degree. If it was going this way, you turn it so that it will go this way. That's angle 180 degree. So either you say reverse the direction or you say turn it by 180 degree. Okay. Question number 32. A metal rod PQ, I like blue. A metal rod PQ rests on two horizontal metal wires. Now, these are the two horizontal metal wires, this one and this one, that are attached to a battery. So this is the battery, this is the positive terminal of the battery, this is the negative terminal of the battery, which simply means current flows this way, okay? And the current will come out from Q to get to P, and then it flows through P and returns to the battery, okay? Yeah, so it's good, it's very important you're able to analyze this circuit. When the switch is closed, once you close the switch, the rod moves to the right. This rod will move to the right. What could be changed so that the rod moves to the left? Okay, this is in line with Fleming's left-hand rule, the force on the current carrying conductor that is placed in a magnetic field. Okay, direction of field downwards, right? Good. Direction of current outward okay, from the book, and direction of the thumb will be to the left, in line with Fleming's left hand rule, okay. The camera is rotating the direction of my hand. Okay, that's how I have to switch to my right hand, okay. Initially I was using my left hand. Okay, but because of the camera, so you see this as my left hand, okay, because of camera. So the field points downwards, right? In line with Fleming's left hand rule, field points downwards, current points towards you, okay, from inside the book towards you, and then the thumb points in the direction of the of the motion to the left, right? Good. So what will you change? What could be changed to make the rod move to the right? Let's see the option. Open the switch. Of course, now when you open the switch, there will be no force. Reverse the battery terminals and exchange the pole terminals. No. If you reverse the battery terminals and you exchange the pole terminals, the direction of thumb still remains unchanged. Let's see. Reverse the battery terminals, but without exchanging the poles of the magnet. If you reverse the battery terminals, so reverse the battery terminals, switch it so that this becomes the negative terminal and this one becomes positive. So when you switch the battery terminals, what happened? In that case, current will be flowing in the other direction. Current now start flowing this way. And when that happens, what will be the direction of force? Use Fleming's left hand rule again, okay? So if you try Fleming's left hand rule, field downwards, right? Yeah, field downwards, current will be outward. Yeah, good. This is what we should have. Field downwards, current will be towards the book, okay? And direction of motion will be what? To the what now? Direction of motion will be which way now? Direction of motion will be direction of the thumb, okay? Which is which way? Which is this way, okay? Motion will now be this way. You get it? Motion will start going this way, this way. So that's the way, that's the only option, okay? Option C. Okay, when you reverse battery terminals without exchanging the poles. So actually the concept is that once you change one thing without changing the other two, direction of motion will change. If it's only one thing you are changing, direction of motion will change. But if you change two things, like this option B, reverse battery terminals and exchange poles of the magnet, then direction of motion remains the same. Turn the metal rod around, so P and Q exchange. When you turn this metal rod around, you've not done anything because it's a conductor and it will always be a conductor. It does not have a positive terminal and a negative terminal. So turn the metal rod around makes no difference. Okay, that makes option C the correct answer to question number 32. Question number 33. A transformer in a computer is used to transform the mains voltage to 240 volts. Mains voltage, that's the voltage at the primary end. Okay, so voltage at the primary end is 240 volts. Okay, so it's used to transform the mains voltage of 240 volts to 12 volts. So it's changed 240 volts to 12 volts. That means voltage at the secondary is 12 volts. The number of turns in the secondary coil is 2000. That means number of turns in the secondary equals to 2000. The question now asks, which statement about the transformer is correct? To solve this question, let us start by solving the number of turns in the primary. Okay, let's find the number of turns in the primary. This is supposed to be a question mark, not 7. Yeah. So how do you get the number of turns in the primary? You use the formula voltage on the primary, or you use the turns ratio, number of turns in secondary over number of turns in primary equals to um, transformer coefficient of transformation, or you call it voltage ratio, voltage of secondary over voltage of primary. What's number of turns of the secondary? 2000. You say 2000 over number of turns in the primary equals to voltage of the secondary is 12 over voltage of the primary is 240. Now we cross multiply. NP times 12, we have 12 NP. 240 times 2000, that will be 480,000. So to solve this, NP, number of turns in primary, will be 480,000 divided by what? Divided by 2000. These three zeros. Sorry. This is 12. The denominator should be 12 divided by 12. Yeah. What did I do? I just divided both sides by 12. Okay. If you divide both sides by 12 here, divide this by 12, divide this by 12. 12 will cancel 12. So number of turns in the primary end will be 480,000 divided by 12, which is what we have here. So you take your calculator and you press 480,000 divided by 12. What would that give you? That gives us 40,000. That means the number of turns in the primary end is 40,000 turns. So let's see the option and let's see what the question requires of us. Which statement about the transformer is correct? A step-down transformer. Yes, something that is stepping voltage from 240 to 12. That's a step-down transformer. That's correct. It is a step-down transformer. What else? And has 100 turns in its primary coil. That's wrong. Not 100 turns in the primary coil. It's 40,000. Let's see. It is a step-down transformer and has 40,000 turns on its primary coil. Option B is perfectly correct. Question 34. In alpha particle scattering, alpha particles are incident on a thin metal foil. Okay, I think this is in line with Rutherford experiment. Let me open the simulation. So, what are you to do here? You are to state which row describes the result from the experiment and the conclusion that the results lead to. A. Most of the alpha particles pass straight through this foil. And what's the conclusion? Most of the atom is empty space. Is that correct? Yes, that is correct. Why? Because in the experiment, when you switch on the alpha particles and alpha particles are bombarded through this gold foil, what happens at the other end? Most of the alpha particles pass through, okay, except the ones that are colliding with the nucleus. Look at the ones that collided with the nucleus. Look at this part. So any particle that collides with the nucleus or that moves so close to the nucleus will be deflected, okay, and that is because the nucleus has a heavy positively charged the nucleus is heavy and positively charged because it contains protons. Fine, but most of the atom is empty space. These are the electrons. But look at the entire empty space that is inside this atom. So Rutherford experiment helps us to understand better what is happening in the atom. So it helps us to know that most of the atom is empty space. A is the correct answer to question number 34. We go straight to question number 35. Question 35 says, alpha particles, beta particles, and gamma ray are emitted by radioactive nuclei. When they decay, which emission can be deflected by an electric field? Alpha particles, beta particles, gamma rays. What's the charge on alpha particles? Alpha particles is a helium nuclei. Helium with a charge of +2. Beta particles is an electron, while gamma rays are just rays of light with no charge. So alpha particle is positively charged, beta particles are negatively charged. Hence, they can be deflected by an electric field. Okay? And if you have an electric field, this is the positive charge, this is the negative charge. If you send alpha particles through it, since alpha particles are positively charged, it will follow this path because it will be avoiding the positive plate and moving close to the negative plate. And if you direct beta particles through an electric field, it will follow this path. Why? Because it will be attracted, beta particles are negatively charged, electrons. It will be attracted by the positive plate and be repelled by the negative plate. So that shows the path through which electrons, which are beta particles, will follow, and then what? And helium nuclei, okay, which is alpha particles. So the one below represents the path the alpha particles will follow, and the one above represents the path the electrons, which are beta particles, will follow. So alpha particles, beta particles, gamma rays, no. Alpha particles and beta particles only. Yeah, these are the only two that can be deflected by an electric field. We go straight to question number 36. Question 36 says, radioisotope X decays to the stable isotope Y. The graph shows how the mass of Y present in a sample varies with time. Which time interval gives the half-life of X? So this shows the mass of Y, but it is X that decayed to form Y. So that simply tells you that if the mass of Y is increasing continuously, it's because the mass of X is reducing continuously. Why? Because it is X that undergoes radioactivity to form Y. So if Y is becoming abundant, it simply means X is getting fewer and completing diminishing. Okay, so look at the slope. Y is becoming abundant, okay, mass of Y. Let me label this graph Y. Let me use color black to represent Y, okay. So if this represents the mass of Y, and then I want to use color blue to represent X, it's simply because X is reducing in amount, okay, till X completely finishes. This should represent the graph of X, okay. That is what always happens. If you add the quantity of X plus quantity of Y, you always get the total amount to be fixed. So this is the concept of radioactivity, okay, and that's what happens during radioactivity. So which time interval gives the half-life? Half-life is the time taken for half the radioactive element to decay, or for half for half the radioactive element initially present to decay. Okay, yeah. So the half-life will just be the time taken for us to get to m/2, which is T2. That makes C the correct answer. Okay, and at half-life, the um, number of moles of X um, that's decayed will be equal to the number of moles of Y that has been formed, provided that no um, no one is being removed. The reaction is taking place in an isolated environment. Question number 37 in an enclosed chamber. Number 37, which particle is absorbed by a nucleus to cause nuclear fusion? Nuclear fission. Nuclear fission, what is nuclear fission? That is when you have a very heavy nuclei splitting into two. Yeah, it splits into two. A typical example is uranium. And what can cause it? That is caused due to when the nucleus becomes unstable. And what can make the nucleus unstable? When you fire it with a neutron. Okay, when you fire it with a neutron, it becomes unstable and it splits into two, which makes option A the correct answer to question number 37. Okay, now we go straight to question number 38. Stay tuned, we are almost through. Ensure you subscribe to this channel, okay. After subscribing, then you can decide whether to join um, my free revision class, okay, which will be taking place 3 days to your exam. Yeah, so ensure you just send me an email so I can have your email address and add it to our Google Classroom. Which 38, it is summer in the northern hemisphere of the earth in June. Summer, that means sunny, bright, and hot weather. Which statement explains why the earth is closer to the sun in June? No, we are focusing on the sun, on the northern hemisphere. Let's assume this is the sun. Let's assume this is the sun, the giant, okay, and this is the earth. This is the equator. When do we have summer? We have summer in the northern, we are focusing on the northern hemisphere. We have summer in the northern hemisphere. When this northern hemisphere is facing the sun, this is the um, axis of rotation of the earth. So for us to be having summer on the north, this axis of rotation of the earth should be pointing towards the sun. I mean, it should be tilted such that the north pole faces the sun, okay, in comparison with the other parts of the earth. Okay, yeah, this is the northern hemisphere. This is when the northern hemisphere experiences summer because it receives more sunlight in comparison with the southern hemisphere that experiences more of darkness. Okay, imagine what the summer hemisphere will be going through during the rotation of the earth. So let's see. The earth is closer to the sun in June. No, the earth spins on its axis in the opposite direction. Of course not. The moon is full in June. Come on. The north pole of the axis of the Earth's rotation is tilted towards the sun in June. Excellent. That makes option D the correct answer to question number 38. We go straight to question number 39. Which statement about the sun is correct? The sun is a dwarf star. It's not a dwarf star. Consisting mostly of hydrogen and oxygen. Of course not. The sun is a giant star consisting mostly of helium and carbon dioxide. Of course not. The sun is a medium-sized star. Excellent. Consisting mostly of hydrogen and helium. Perfect. The fusion of hydrogen atoms causes the formation of helium. Okay. So most of the gases we find in the sun are hydrogen and helium. And by the way, the sun is a medium-sized star. It's not a giant, it's not a dwarf, it's not a supergiant. Question number 40, the last one. The table lists some information about some stars. Which star will eventually explode as a supernova? Name of star, algebra, name of star doesn't matter in this case. Okay, what we need to analyze is what we have here, the type of star. Okay, then we can also um, we might put the temperature into consideration. Fine, but the most important thing is the type of star. We have red giants. Yes, a red giant that let me open the life cycle of a star, okay? But the most important thing is that when it comes to a star exploding, is the red supergiant. During their life cycle, the red supergiant will um it will explode at some point, okay, to form a what? To form a black hole. Okay, when it explodes from a black hole, then the supernova created can then can then move and spread out. Okay, when it spreads out, some of the when it explodes, the supernova formed will spread out, while the core will collapse into the black hole. Okay, when it explodes, rather the the core the core will form a black hole, fine. While the gas, dust and gas that explode, that forms, that goes out from there, what happens to the dust and gas? The dust and gas that goes out from there, some of it will still gather together to undergo the lifestyle cycle of a star, okay? Come together, expand, collapse again, and form eventually form another star, okay, but it won't be a red supergiant as big as the initial one, okay, because it will form a smaller one because it's like combos of cake, like combs of cake. Yeah, you can still pack them together to form a smaller version, okay, a smaller cake. Of course, um, not what anybody would do actually. But that's just an illustration, okay? Yeah. So look at this represents life cycle of a star, okay? The interstellar nebula. Yeah, that dust and cloud. Interstellar nebula form a protostar, okay? So if the protostar is a big one, it can form a red giant, okay? And it can also form a red supergiant. If it forms a red supergiant, it will eventually become a supernova. This supernova will then explode. During the explosion, the gases that that spread out, the gases that spread apart from the explosion can eventually become another nebula which goes through the life cycle of a star. Okay, but of course, it won't become a red supergiant. So while the supernova form can either become a neutron star, okay, that glows white, or it just becomes A neutron star that glows blue, or it just becomes a black hole that has extremely high density and whose gravity attracts anything close to it. The gravity even attracts light and bends rays of light. Okay, so I hope to see you. Please ensure you subscribe to this channel before you reach out to me to add you to the revision class. Okay, so when you are added to the Google Classroom, Physics for Everybody, then we'll have a free of charge. Okay, just as my contribution to the society. Thank you very much for watching this video. Extend my regards to your classmates and your teacher. Do have a nice day. See you on the next video. Goodbye. I wish you excellent grades in your exam.